Ladies and gentlemen, good evening. So in this session, I would like to talk about the development of load balancer, and also I would like to talk about the software engineering that supports LINE-original LBaaS. So this is a last session, therefore I believe that you're tired. However, please listen to my presentation. I'd like to introduce myself. My name is Hayakawa. I joined the LINE Network Department as a new graduate in this year, and I'm working for the development operation for the load balancers. And today I would like to introduce about the load balancer. And before that, let me first talk about how the services that we are developing our position in the LINE infrastructure. Our load balancer service is on the LINE's private cloud components called Verida. And Verida is an OpenStack-based cloud service that has been operated within LINE since around 2016. And many LINE services, including LINE itself, run on this Verida. And currently, LINE has been migrating from traditional infrastructure to Verida, and now it has become 1,400 hypervisors and 35,000 VMs. Therefore, it's becoming a large platform. In addition, last year, we have added a new 20,000 VMs that have been created last year. And Verida currently offers a wide variety of services, for example, computing and networking. Those are the basic infrastructure resources. On top of that, we provide the Kubernetes and Kafka, that is the middleware, and also function as a service are being provided. The load balancer that we are developing is positioned as one group of a group services called as EAS in the same line as computing and networking. The role of LBaaS in Verida is to provide a highly scalable load balancer services for various line services. And developers can use the abstraction provided by LBaaS as if the load balancer is dedicated to that services. However, in reality, resources are cut out from the load balancer cluster common to all services. Therefore, our role is to develop and operate this common cluster and API server provided to developers. So LINE has a very wide variety of services. Therefore, it is not possible to satisfy a wide range of needs by providing a general-purpose load balancer. For that reason, we provide two more types of load balancer services. One is what we call it as L7 load balancer. This is a so-called a reverse proxy. So load is distributed in units of application requests based on the HTTP path and header contents. The other is an L4 load balancer. This is a load distribution at the TCP connection level based on the information such as IP addresses and port numbers below the application layer. And there are two types depending on use cases. The L7 load balancer has rich features compared to the L4. For example, TLS termination, fine-grained load balancing at the HTTP level, and request filtering. Those are the purposes. So this is often used for the general web applications in order to fulfill the use cases. However, for the workloads that require performance such as messaging services and media delivery, for that, L4 load balancer is used instead of L7 load balancer. So what kind of line functions are using our load balance for you can see, for example, if you are in the screen of the messaging function that you often see as a messages and also videos and icons as well as advertisements are using our load balancer service as a traffic. And also, some of the functions of Line family services such as Line Clover and Line Pay are also used. So as I have mentioned, the data usage range expands. Therefore, the number of services that use our load balancer will increase in the future.
で、そのようにすでに重要なサービスの
Well,
ロードバランサーサービスなんですが
load balancer is becoming an important service, but we are not just operating by purchasing pre-made load balancer appliances. We are developing the load balancer service. For example, everything from API servers for users to access load balancer services and L4, L7 load balancing services are developed and operated in-house by software in-house. Especially for L4 load balancer service, it is made almost scratch from the base part called data plane that actually handles user traffic. And why we are developing in-house without using the off-the-shelf products. This is because LINE has finally developed in-house in view of various problems that it has faced while operating off-the-shelf appliances. For example, those are the scalability and also the availability issues and operational costs. So before Builder's load balancer service until 2016, LINE had been using a ready-made load balancer applications. The configuration at that time was where the two load balancers called 1+1 were moved in one set. So this is the active configuration, and many users were using L4 load balancer and configured it to provide L7 LB as needed. And this was the common configuration when SMBs deployed on-premise load balancers, and they were able to operate. However, as the service scale has developed, there are various issues that have emerged. One is the issue of the operational cost. The load balancer was based on the CLI and therefore it is operated manually. Therefore, it was difficult to automate. If the operators are not available, the request is often processed only 2 days or 1 day after the user submits the application. Therefore, for the operator and the developer, it was so stressful. Under these circumstances, LINE has become involved in a variety of services, and there is a strong demand for the load balancer. Therefore, we cannot ignore those operational problems. And talking about the scalability, we had a problem with scalability and availability. That is a session table depletion problem. And this is a problem caused by the implementation method on L4 load balancer. As one of the implementation methods of the L4 load balancer, there are several ways. The correspondence between the traffic distribution destination server and the client is stored according to the TCP, and there is a session tables, and therefore data structure is being stored in this session table. The traditional L load balancer use session table, but there is a weakness in this implementation, and there is an attack called TCP, and therefore they are not able to accept new connections. Therefore, the client's number have been limited according to this scale. Therefore, this is a issue of scalability. And if there is an attacker with a maliciously to use a DOC attack called TCP/CYN flood. Then this attack fills a session table with information that is completely meaningless to the service. And that affects all servers registered in the load balancer. Therefore, there is a problem that would occur in a very, very large range. Therefore, this is an availability issue. So therefore, we reviewed the basis of the load balancer, and there are new 3 requirements. The first is to reduce operational costs for both the developers and the operators. So this is not management interface that assumes manual deployment, but API-driven and human-free form so that the developers can get a load balance when they need it. The second requirement is to be able to scale well with service growth and site traffic growth. And this means that there is a session table exhaustion issue. And also, this means that we are able to have more scalability. And the third requirement is the availability, which means that it's easy to increase the number of load balancers and therefore make it redundant. And also, if there is any kind of event, that impact will be limited. In order to fulfill those requirements, we look at the Google and Facebook load balancers design. In fact, from 2010 to 2016, it was a time when such major companies made announcements about many load balancers in media such as papers and blog posts. Many of them already have an in-house developed load balancer, and also they do have a longer experience of over 5 years of operation. As a result of research, these major companies also have a background that they have developed their own development with a common awareness of the problems that LINE had at the time. Then, when we redesigned the load balancer, it was very helpful as an information. As a result, the multi-tier load balancer architecture had been used. So simply put, this is an architecture that connects multiple load balancers in multiple stages, such as distributing servers with L7 load balancer and distributing the load with L4 load balancer. This is a new architecture. And this architecture is configured to increase availability by making each load balancer tier redundant with N+1 method. Also, even if the capacity of each tier is insufficient, we are able to increase the number. Therefore, it contributes to the scalability. Furthermore, in order to deal with the session table exhaustion problem, the L4 load balancer is a statelessly completely load distribution, and this has made it possible to cope with the increase of clients and also malicious attacks. Furthermore, following the examples of other major companies, L4 load balancer and L7, the functions are implemented as a software on general-purpose server hardware. There are 2 main advantages of creating a load balancer with a general-purpose server hardware. The first is cost is very low. The low unit price means that number is easy to increase. Therefore, we are able to have the scalability and redundancy. So let's take a look at some of the results of the cost calculation. And according to the one request, the unit price, so using the traditional load balancer, so in comparison, it's around 1/10 of the cost being required. And the second merit is that load balancer can be operated as a normal server. This means that you can use the know-how of general server operations like Prometheus and also Ansibles, permutation, and using Docker. And therefore, these know-hows can be used. So actually, our load balancers, most of the components of our load balancer are made up of OSS combinations used in general servers. So I would like to talk in detail about the implementation. The first is a controller that bundles the various components. The controller is implemented as a very simple Python web application. This means that it automatically performs operations such as a load balancer creation, deletion, and setting in response. And therefore, the operational cost can be maintained at low. And also, if the developer requires, they're able to have the load balancer service. And for the developers, developers can directly use the API provided by the controller. However, using this web UI, they are able to use intuitively through that. And API authentication is shared with OpenStack, and therefore the resources can be managed in units such as OpenStack users and projects. And this makes it possible to seamlessly link Builders VMs created with Veritas OpenStack, and also the load balancer's virtual IP address can be used in order to assign domain names. In addition, functions that support user operation are also being provided. One is the revision management of load balancer settings. This is a function for version management of past load balancer settings. For example, if the developer makes a setting error, then it is possible to easily roll back to the previous settings. And next is the design of L7 load balancer cluster. And this figure shows the entire L7 load balancer cluster. We are building an L7 load balancer using Kubernetes. Each HA proxy container running in this Kubernetes cluster corresponds to the L7 load balancer. The purpose of adopting Kubernetes is mainly to use the functions as deployment using containers and service discovery, and such functions as autoscaling. In addition to that, we have roughly divided 3 approaches to achieve high availability by keeping the failure domain as small as possible. One is that there is a redundancy of a Kubernetes cluster. We run 2 Kubernetes clusters with active per the region. And this has 2 purposes. One is that if one entire cluster fails, only one cluster can continue service. And the other is to avoid the risk of failure, such as when upgrading the cluster itself or the Kubernetes itself. If there is a failure, we are able to avoid this kind of risk. With this configuration, for example, 2 clusters can be placed in different data centers to handle failures at the data center level. So we provided the Builder VM for Kubernetes nodes it seems simple. However, as an advantage, OpenStack using Builder has a mechanism to increase the fault tolerance by placing multiple VMs. So the load balancer administrator is particularly concerned about the placement of such resources, and there is no need to distribute. In addition, when building a new load balancer cluster or increasing the operation can be completed without any physical work.
So the third idea is to have a distributed virtual IP addresses. When a developer requests the load balancer creation, the load balancer virtual IP addresses are assigned across the multiple containers based on the policy inside of the Kubernetes. By doing that, for instance, when one virtual IP address gets content-related traffic and also container CPU usage goes up, in this case, because container has dispersed resources, so the impact can be felt within the container alone. And also by using the Kubernetes replication functionalities to create the multiple containers with the same function, by this way, if one node container suffers, the remaining node can really keep the services intact. So let's talk about L4 load balancer. Just like L7 load balancer, this is a cluster of the L4 load balancer in one build region. So L4 load balancer has a very special requirements for the network. So unlike L7 load balancer, it has a server cluster outside of the current builder OpenStack structure. So each server has in the L4 load balancer is supported. So for the redundancy structure, just like the L7 load balancer, this is a redundancy for cluster and load balancer. And also, so all the nodes are using the physical server to avoid the virtualization overhead. Furthermore, here's a data plane. For some reasons, we developed from the full scratch. Why then we have to develop with full scratch? The biggest reason is the performance. The software load balancer compared against hardware appliance, software alone, single unit alone, the performance is inferior because of the weaknesses of the software-based approach. We have to have a lower number for scaling, but when you think about cost, we have to ensure the single unit performance, especially for L4 load balancer. Requirement is that 7 million packet processing per second. So then OSS load balancer, with the then OSS load balancer, it was very hard to achieve this performance level. But in that year, to the kernel, Linux kernel XDP function was added. This is the packet processing framework for application which requires high performance in XDP. Linux can really process at the high speed by running the device driver layer right after the packet is received from NIC. So this packet processing coding is very simple to write in C languages, and also requirement we can write with 500 lines of code. And also, if you use things other than XDP, it's much lower in terms of the code. And also, this XDP is a very good functionality and convenient for us, who are not professionals. But I don't want to deep dive into the functionality. But XDP it can really detect in a static way with the Linux kernel functionalities such as memory access errors. So when you see maintaining the program in C language is quite hard, but with this in functionalities, if you add a new function to the load balancer or maybe change the programming, and if you happen to embed the bug, so you don't have to worry about this at all. So by making L4 balancer by XDP, we were able to achieve the performance. But for product improvement, how can we keep the performance is very important. So the high performance is a service value for the users which are expecting of L4 balancer. Especially with a new function implementation, the code is changed. In this case, we have to be aware of the lost performance immediately. So we need to really measure the performance using the CI/CD to ensure the quality of the code. So we did the automation for the performance test. Why do we have to automate the performance test? Because of the repeatability of the performance test. Each individual in the developer does the performance test according to his own procedure and share the result. That's okay. However, actually, the test environment, the parameters are different from one from another, and we cannot really compare apple to apple. So avoid that situation. We prepare for the common test bed so that we can automate the provisioning and testing in the test bed. And also, we make a performance test is triggered via the automatic CI/CD platform from the GitHub pull request because we can put this test in the development flow. This way, we can really have a continuous performance test. The test content is, of course, a simple measurement for the throughput, but we have to measure the rate which does not lose any packet. And also, if the client has a multiple simultaneous connections, we have to measure it. And also, the test with the TCP SYN flood attack should be the scenario. So the test result is automatically aggregated and also made into the report as a pull request comment. And for the raw data, we always store them. So if you want to see what happened, the data is available. So up to now, I talked about the homegrown development for the load balancer and also engineering or structure to ensure the quality and so on and so forth. From here on, I would like to talk about the recent activities of the use cases in actuality that we added new functionality because of the request. This is my first task when I joined the LINE, so I would like to really have a deep discussion in terms of technology as well. So I talked about making the L4 load balancer stateless. So we were able to solve the session table depletion problem. However, with this stateless implementation, we created new problems. The problem is that server graceful shutdown cannot be done, and also it's hard to have a failover functionalities. So I'd like to give you a concrete analog talking about the use case for this. So where is the root cause for this problem is that maybe storage L4 load balancer methodology for implementation. We adapted the implementation is that was the algorithm to decide the server destination addresses by taking out a hash list based on the protocol number and the port number and IP address. By doing this, we can really decide the server destination by calculation because we have a packet information and also we don't have to really have any information stored and we can make it stateless. So if the server admin would like to update the application and would like to shut down server A, in this case, server A has to be a hash list has to be updated, removing server A for general operation. So we have to stop the server A new connection, and also the client which is already connected to server A, we have to wait until the session is completed before shutting down. This is a graceful shutdown operation, but with a stateless load balancer, we cannot do this operation because it's stateless. So there is no TCP session information in the load balancer. So this is one of the problems why we cannot really perform graceful shutdown. The other problem is when the hash list is updated without server A, and also other existing connection can be interrupted. In this case, the packet which was going to server D was going to be transferred to server B all of a sudden. And also, if the client is already connected to server D, because of the server B, the connection will be disrupted because in the views of server B, the client is unknown to that. So this is why the failover is quite difficult. But this is a well-known problem, so we took measures when we designed it. So by using the consistent hashing with a very special method, we are able to lower the probability to have a change of a packet destination after and before the hash list updating. Based on the advanced research, we knew this, so we used consistent hashing algorithm, which is maglev hashing, which is used for the Google load balancer. But for reliability, its use case is insufficient. And so one is that media platform application which uses the media, video, and also images of LINE application. For instance, if when you try to upload the images in the LINE and it's already cut, all of a sudden you cannot do it. And if you are seeing the video, connection is interrupted and the video stops. You don't like that, right? So we want to avoid this situation. We need to have consistent hashing. Reliability is not enough. The other use case is that ads platform, which is used for LINE ad display. So advertisement display is very important, but it really leads to profitability. So if the connection is interrupted, you may lose the advertisement impression. This is our concern. So this problem was an obstacle when we migrate from the infrastructure, from the traditional infrastructure to Builder in the media platform. So we decided to have some improvement to the load balancer to solve this problem. The solution we had is a session caching methodology. And so this is a methodology to store in the cache, which is called session cache of the destination, which is obtained by the host. So for load balancer, first searches the session cache. If it had a cache hit, and it's going to transfer the packet to that. If it misses caches, it will decide the server to this destination server on the hash list. So how do we solve this problem of the stateless load balancer? So session cache entry, when the server is service out interrupted and also hash list is updated, still the second session cache entry is surviving. Maybe we can avoid the interruption between the client server and the connection. But you may notice already, so with this session cache, it has the same problem as the session table depletion problem, which was the problem in the load balancer operation. So the more client which are concurrently connected, session capacity is pressured. And also if you have a TCP SYN flood attacks, then depletion is triggered. So the problem that we faced was by making the load balancer stateless, maybe we can really avoid session depletion problem, which is benefit, but the failover and the graceful shutdown is very hard. But if we have a session cache using the stateless state, then it will weak against SYN flood attacks, even though you can do the graceful shutdown or failover. So to this problem, we selected hybrid methodology to use stateful and stateless accordingly. In the peacetime, we operated the load balancer in a stateful mode. But if the SYN flood attack is detected for a certain time period, it will go to the stateless mode using the consistent hashing. So to detect the SYN flood attack, we use the feature is that a lot of SYN packet is coming in a short while. So inside of the load balancer, we measure the SYN packet rate, and also if it goes to the threshold value, then we decide this is a SYN flood. This is the algorithm we use, but we keep the stateful implementation where we can do the graceful shutdown and failover. Yet it will strong against SYN flood attack. So it took 3 months to implement it, and we transit to the production environment. And also the media platform team which requested this functionality, they finished the validation and also they migrated to the service to the builder. So we implement necessary functionalities for each application. This way we can really have a development which is flexible but very focused upon line service. Where I'm going to talk about what we are going to do from now. So as one of the feature, currently Builder team is developing the integration with the managed Kubernetes. So we use Kubernetes to structure L7 load balancer, but currently we use our own Kubernetes for operation. And also by building this on the managed Kubernetes, operation will be even more efficient. And also Kubernetes has a load balancer, external load balancer to disperse it. So we can use our own developed load balancer for that. It's one of the use cases. So for this managed Kubernetes services, the session is already completed, but Nishiwaki-san from Builder team can explain to you well. If you didn't participate in that, he will be updated in the YouTube. So please watch that. Another activity is that we have a multi-tenant network support, which is new to us. So to this network, we use SRv6 protocol. And also, the current load balancer implementation is not supporting SRv6, but we have to support in near future. SRv6 is a comparatively young technology, and also we don't have much use case for the load balancer application. So that we had to do that too. So new network architecture using SRv6, the session is already completed, but the Builder team, Mr. Tsuchiya, did the presentation, so see the video afterwards. So lastly, last year in 2018, load balancer world, it was a great year. GitHub and Facebook, they open sourced their own load balancer as OSS, and also they adopted load balancer literature of the CDN operator of Fastly in the conference. And among them, there is great useful knowledge for us. So we are going to incorporate these kind of knowledge and experience into our implementation. This is a list of the literatures that I used for this presentation. If you are interested in, please go to the site. And after this session, I will be in the Ask the Speaker corner. So if you are interested in this, and I'd like to answer your questions or maybe talk with you, so please contact me. Thank you very much for listening.